Hi, welcome to the next channel. So what I got here is a MIPS based processor board, which is a Dragino V2 board. So this I got it around a couple of years ago for some kind of development. So let me show you the board before we start this episode. So this is the board. As you can see here, it comes with this package and it has this power supply and then the board itself. So this is meant for IoT applications, and then it can be also used for networking applications. It can be used as a CPE and stuff like that. As you can see, it has two Ethernet ports, and then it has also a phone jack, as you can see here, and then it has this power port. So the interesting thing about this board is it is extremely low power, and as far as I have measured, it is consuming even lesser power than Raspberry Pi V2 board. So its performance is also quite less if you compare with Raspberry Pi. It's far too less. So once I have benchmarked the same in my TrueBench software. So in case if you guys are curious about TrueBench, you can go there, you can explore the same, and you can also download my source, or else you can download the binaries and you can benchmark your processors and according to the instructions, of course, and then you can send your results. So if you go here, I have listed various benchmarks. Some I have included on Raspberry Pi 3. Some people have contributed, like this NanoPi and stuff like that. And you can see here the last benchmark is nothing but this Dragino V2 board. It's a processor called AR9331. That's the processor, Athros processor, and it's a MIPS processor. Once you go through the datasheet and other specs, you can find that it's a MIPS based processor. So the MIPS processor is an example, just like ARM is also in RISC based architecture. So which means it contains a reduced set of instructions, something you compare with x86 platform like this laptop, where it is based on CISC based architecture, which also stands for complex set of instruction sets it contains. So the difference, if you see the RISC and CISC, is as the name says, it will contain reduced set of instructions. So in a way we can understand, I have a large jar of this Lego bricks. So let's assume this is a processor, and each of this block represents each of these Lego blocks represents instructions, machine level instructions for this processor code. So if you compare a CISC versus a RISC based processor, so let's assume this glass full of bricks is your MIPS or ARM processor. So this is going to be the instruction set for the same. So each block, once again, it represents each instruction for the same. So as you can see, for given processor or architecture, you will have an increased amount of instructions for a CISC based architecture. The reason is they are kind of getting these fundamental instructions and they are building complex set of instructions. That's why the name CISC also stands for. So apart from that, there is also an important difference you should also understand, because this is not something I want to take like the way they cover in your college textbooks or some kind of boring theory. So it is quite interesting. So if you see here, each of these instructions are far more fundamental level versus this, because each of such instruction can comprise multiple amounts of such basic fundamental instructions. So which is the reason you have instructions for you have abstracted instructions, you have also some instructions which can do several tasks. So this way what happens is you have one instruction, if you execute in this processor like CISC based x86 processor, you may have several CPU cycles, and you cannot predict how many CPU cycles it may take, and it may complete that particular instructions. Whereas in this instruction, since these are very fundamental instructions, at the max it may take a couple of CPU cycles or just one CPU cycle to execute per instruction. So this way when you compile the code of your ARM processor versus an x86 processor, the code compiled binary file can contain less amount of code in this case, because what is happening is you are cramming up several instructions. When you write in C code or C++ code, you are cramming up several instructions into few quantity of instructions, and in that way you have several instructions in this particular architecture like CISC versus this. So in this case, if you compile the code, what is happening is the compiled code is going to generate a large more bigger size binary file, because each of such instruction comprises basic fundamental level of instruction, something compared to a CISC based architecture. So this is the reason when you do an image search of CISC versus RISC, if you do an image search, let me just keep this aside, CISC versus RISC, and if you do an image search, you can find various interesting images. So you can see here a RISC based instruction contains very simple instruction execution, that's it. Whereas in the case of CISC, you may have machine instructions like I showed in the jar of instructions, but inside each instruction you may have again a microcode, and it will break down to some fundamental level instruction. So eventually what is happening is, to implement all this stuff you need lot more hardware footprint, and basically you need lot more transistors and physical hardware. So which is the reason the processors something when you compare with this or your Raspberry Pi or your mobile processors, let it be Snapdragon or let it be Qualcomm or anything like that, when you compare that with something like x86 based processor, the processor size is going to be significantly large, and as it's it is going to comprise of more transistors and other circuitry. Obviously its footprint, as it gets bigger and bigger, it is going to consume more power and other resources. So this is the reason CISC based processors needs lot more power traditionally than you compare with RISC based processor. So this is the reason this is more suitable for mobile applications, and it is more suitable for such low power application. This is not a mobile application, this is an application meant for low power application, so something like that. So that you don't need to reduce the die size of these kind of processors, let it be manufactured in 22 nanometer lithography or 32 nanometers or whatever it is, but you don't need to reduce the die size, but still you will get the efficiency of power consumptions with this sort of architecture. But there is a drawback. What is happening is you may have the same code, as I said, the compiled code, as it uses these set of instructions. For any specific set of lines which you write in C, you may have lot more instructions, so naturally its code size is going to be larger, and it is going to just iterate again and again through these instructions, versus a case like CISC. It may replace a couple of lines of your C code with a couple of lines of your CISC based processor instructions, but that may not be the case if you compile it with a MIPS cross compiler or ARM cross compiler. It may need several instructions to replace your couple of C instructions, C statements. So that's what it is. So this way, as I said, you need lot more hardware footprint, and this is what, anytime you search a comparison between a CISC and RISC based processor, these are the various aspects they cover, but they talk far too technical and they make it things so boring, but it is not like that. It's very simple. So let me go back to this image. So if you see here, if you go to the data sheet and other things, you can understand it consumes somewhere, I think they have changed the link when I was, so you can go through various data sheets, its PDF, and you can see here some of the specs. Its frequency, the CPU frequency for this board is 400 megahertz, and energy saving is just 200 megahertz, and you can see its various other specs. So if you see the power consumption, you can see it's 120 milliamps and 60 milliamps. It is just very less something. If you compare this with any sort of x86 of this size, but you get also added advantage. x86 processors or CISC based processors also do well in terms of performance. They do perform well, and you can definitely see here when you compare any of these processors with Intel Atom or any such processors, you can see there is a lot of performance gap. Let's take example like Raspberry Pi 3. So please bear in mind this TrueBench is a very simple benchmarking tool which I did, and I did for a very specific purpose. There is no absolute debate about the same. I got sometimes opinions from core software developers saying that it doesn't have any much code and it doesn't give any sort of full idea on. Let's go to the download page and let's open this code. So this is the code I wrote. I wrote around a year ago. So you can see here it has been done long time ago. So if you see the code is fairly simple. The reason why I am pulling this is you need to definitely let it be any architecture. End of the day, it boils down what the CPU can do. If it doesn't do anything, then what is the use of that specific architecture? You cannot take a mobile processor and then dump it in a very large server based platform like that. You need definitely a processor should perform as well. Just not saving power is not end goal. So in that way if you compare with the tools like this, you need a tool which can compare directly a specific hardware with another hardware. Unfortunately I'm unable to find any existing benchmarking tool which can do the justice, and at the same time we need to have also an open platform, because we should able to compile the code. Tomorrow if some new hardware comes, we need to have the code, and the code should be simple so that you don't get much compiler optimization and stuff like that, so that it is not, the results are not deteriorated or polluted. So this is the reason I have done this code. I kept it as small as possible. The objective of this code is not checking all that CPU instructions and figuring out which CPU is faster and stuff like that. The objective of this code is to essentially check a single dimension measurements, means single core performance, and completely ignore the multi-core performance a single core processor core performance. And essentially what I want is I want to check the bandwidth of RAM and the data logistics or data transfer bandwidth. So this is what it is. So if the processor is very small, something like this, its cache is going to be very small, and essentially when you do such iterations, you can see here I'm doing around 1 million iterations. So when you do such quantity of iterations with large buffers, so you need to move a lot of data between your RAM and CPU to and fro in a case like this board, or let it be Raspberry Pi or anything like that. But essentially this is not the case if you run the same code in a large Xeon processor, because if you go back and let's compare a couple of specs. Let us take a Xeon processor. You can see here, let's pick this Xeon processor, and let's pick some laptop processor, something like that. You can see here, than this Xeon processor, the TrueBench score is much better in a case like a laptop processor, because you should always understand desktop processors and laptop processors per core performance will be far more better rather than anything like a server based processor. The reason is server processors are meant to do bulk transactions, and it is meant to do bulk data crunching. So this is what it is, whereas in the case of desktop processor, it is meant to do a few set of applications, but they should run at that highest possible performance. So both the roles of a desktop versus a server is completely different. So this is the reason each core, the desktop may have few cores than you compare with a Xeon or even the newly AMD EPYC or such processor. If you compare with even an EPYC with Ryzen, you get that difference. So desktop processor is always going to outperform a server processor in terms of its per core performance. But if you do any multi-threaded applications, obviously server processors are going to do much better, because it has lot more cores to handle such bulk processing loads. Also, one more interesting thing which I forgot when I was recording the main video is, if you check the cache, CPU cache of a desktop processor, a laptop processor versus something like Xeon, you can find Xeon processors will have lots of cache. You can see here it has around 30 MB cache versus something like a laptop processor which has 8 MB cache, and even this specific desktop CPU cache, which is also an 8 MB cache. So this is an important factor. This also affects the per core performance. The more CPU cache you have, you get better performance whenever it comes about transactions between CPU and your RAM. So that way, if you take an Xeon processor, and let's take this even a simple laptop processor, and if you compare the same, you can see it has this is a Xeon V3 processor. So this has less cores, and this laptop also have 4 cores. But let's take an example of some other Xeon based processor. Let's take Intel Core Xeon. Yeah, if you see this processor, it is so much underperforming. Please note the TrueBench benchmarks are latency benchmarks. So lesser the bar size or lesser is the amount of time taken, the faster is the processor computational power or per core computational power. So if you see that way, this processor has 12 cores and 24 threads, and this has a score of around 141 million versus this specific one. This is a laptop processor 4910MQ. Versus this laptop processor, which is 4910MQ, and it has a score of around 75 million, as you can see here. So this what is quite interesting when you explore TrueBench. The reason I am again discussing TrueBench is essentially, no matter what type of architecture you have, you need to find its performance in relationship with respect to its consumption of its other resources like power and other stuff. So this is the reason I'm just discussing about the same. So TrueBench, if you are interested, you can explore the same. Please follow the instructions and you can submit your score, and you can download readily compiled binaries, or else you can compile the binary as per the instructions. Again, I'm going to stress the same. So before I wrap up, we can just quickly hop on once again to this home page, and then we can just do a quick analysis. You can see here, this is the performance curve of Raspberry Pi 3 versus Raspberry Pi 2, and you can see here it has around half the performance or else it has the double the performance of Raspberry Pi 2, or else Raspberry Pi 2 has half the performance of Raspberry Pi 3. Again, you can see various other benchmarking tools as roughly the same. So this way what you can do is, if you have different architecture processor boards, let it be a MIPS or ARM or x86, or else let it be a MIPS processor and ARM processor, you can do benchmarking of the same, and you can also see a specific code when you compile. You can also check how much is the amount of binary file it generates, and again this is the reason you get that difference in size of the binary files, because GCC need to optimize it as per that processor hardware. So GCC has to do a lot more optimization when it comes to RISC based processor, something like this kind of boards, because it has to generate a complex C language instructions into fundamental instructions, and it has to do that optimized level of code generation. So this is what it is, versus something if you compare with x86 based processor. So there are so many things involved. So this also decides the factor of ALU size of your processor, and lot of complexity involved in the same. So again, as I said before, the hardware footprint is going to be more if you design CISC based processor to handle all these instructions. You need a larger footprint of hardware, you need more transistors, you need to drive this hardware and to drive this circuit. Obviously you need a lot more power and the complexity involved versus something like this. So this also tells in case if there are any bugs in the hardware, you may get lot more bugs in this case. So that is the reason sometimes Intel may have some kind of security hole and other stuff, because it's a lot more complex to deal this stuff. And whereas in case something, if you design a RISC based architecture, the complexity of maintaining the code, maintaining the architecture, CPU architecture and other stuff is significantly reduced. Let's not always think about the power consumption factor alone. Let's assume you are designing an ARM or MIPS processor for a server based infrastructure. So in that case, the processor doesn't have to deal a lot of complexity in terms of its design and architecting of the same, versus something if you compare like RISC based processor. So there are a lot of factors involved. There are, other than this whatever I discussed, there may be its own you can find its own advantages and disadvantages between each architecture. Sometimes you get issue of performance, sometimes you get a requirement of saving a lot of power for any IoT applications, and including sometimes it can be application in space, research and satellite based applications. So it's a complex topic. We cannot say that conclusively one architecture is better than other or something like that. It all depends on what is the specific requirement. Assume you are designing a very large supercomputer or something like that. Sometimes you just need top-notch performance, and you are okay to kind of spend money in terms of building the hardware resources and driving that machine as well. So you are prepared for both capex and opex as well. Capex means the capital expenditure and opex means the operating expenditure. So operating expenditure is your electricity consumption, and then you recruit various engineers to take care of the same, and then you deploy it in a data center, and you need physical infrastructure and cost like that. Whereas the capex is the initial purchase infrastructure costs is capex. So it's both these things are involved. It's just not something as a software developer, if you think about the RISC and CISC architecture, you can quickly conclude, I like this particular architecture, I don't like CISC architecture, something like that. But there is something beyond that. If you are thinking like an entrepreneur, there is something beyond that. There is something like a need, and then how a specific architecture addresses that specific need. If you think about RISC, it is addressing the mobile device market cap, whereas if you think about CISC based processors, it is currently addressing data center applications. So this is what it is. So hope you guys loved watching this video. In case if you have anything to discuss, or if you have any questions, be in touch in email. So thank you once again for watching this video. Have a nice day. Bye bye.